Good morning. I hope you guys had a chance to sleep in today. I just wanted to take a couple minutes to finish the notes that we started in class on Tuesday. Just so that when we get back to class on Tuesday, we can just spend a little bit of time practicing some of these. We'll start the 3.2 notes also, but anyway, this at least we'll get to start on practicing these. So just a refresher, when we ended class last time, we had just said that first of all, we had defined what critical numbers are. Those are spots where the function has a derivative that's either equal to 0 or the derivative is undefined. And again, our examples were, for the derivative being 0, you're going to just have a nice smooth curve, and it's going to be at one of these points where it's either a max or a min, most likely. Or where it has a derivative that is undefined. And again, our example that we looked at was an absolute value where it had a sharp turn, but there are other cases where the derivative can be undefined, specifically when we end up with a vertical tangent line. We've looked at those in class before, but that was not one of our examples in class on Tuesday. But again, this occurs when we have a function that has a fractional exponent between 0 and 1. So that when we take the derivative, the exponent becomes negative. The variable ends up in the denominator, and we end up with some spot where it's undefined. And again, there are places here where we would have a derivative of 0 where it's not at a max or a min. Most specifically when we've got some function that looks like this, where we would have a horizontal tangent line, but it's not a max or min, but that's still a critical number. We still need to investigate it. So what we had talked about was that if we're going to have a relative max or relative min, it can only come from this pool of critical numbers that we find. All right, so then we started to say, okay, so if we're going to find the extreme on a closed interval, then let's find that collection of points, right, the critical numbers. So we've got a continuous function, it's on a closed interval, and so it says, first thing that we're going to do is find all of the critical numbers that are in the open interval AB. And then these two kind of go together. We're going to take and get all the numbers that we've got from our pool of critical numbers. We're going to take our endpoints and we're going to evaluate f at all of them. And then one of those we will select for the minimum. It's going to be the one with the smallest value, and then the greatest is going to be the maximum. And so we had started this one in class on Tuesday. And so let's just do a refresher here. We checked to make sure that f was continuous. It's a polynomial. It's continuous everywhere. So specifically, it's continuous on this closed interval. Right? Then to find the critical numbers, we took the derivative. We got 12x cubed minus 12x squared. Again, we're looking for where this is 0 or undefined. Never going to be undefined because its derivative is also continuous everywhere. So we're just going to take and set this equal to 0. And what we ended up with was 12x squared times x minus 1 equals 0. So our critical numbers were x equals 0 and x equals 1. We just do a quick glance to make sure that these two values are actually in the interval that we're given. They're still critical numbers no matter what, but we just want to focus on this interval, right? So let's say this had been 3. We would say, yeah, that's a critical number, but it's not in our interval, and so we would cross it out, all right? But we are going to take these two, and I believe that we had gotten to the point maybe where we were setting up an xy table or an f of x table. And so I'm going to put those values in. I'm going to put -1 as our first endpoint, then 0 as our first critical number, 1 as our second critical number, and 2 as our other endpoint. And then we're just going to plug them in. All right, so again, don't forget to go back to the original. Right? So we've got 3 times -1 to the 4th minus 4 times -1 to the 3rd. This is going to be +3. And here, this -1 to the 3rd is going to stay -1, times that -4 is going to be +4, and so we end up with 7 right here. We plug in 0, that's pretty easy, we get a 0. We plug in 1, that's pretty easy, we get a -1. And then for 2, we've got 3 times 2 to the 4th minus 4 times 2 to the third. 2 to the fourth is 16 times 3 is 48. And then minus, whoops, sorry, this should be a 3. I think I said 3, but wrote 2. If not, sorry about that. All right, so 2 to the third is 8. 8 times 4 is 32. So we've got 48 minus 32, which gives us 16. All right, we look over all of these values that we got, and we pick the smallest one to be the min and the largest one to be the max. And so we're going to say the absolute max on -1, 2 occurs at the point 2, 16, and the absolute min on -1, 2 occurs at the point 1, -1. And that's it. All right. So then for number 3, again, this is what I was mentioning just up above about how we have a fractional exponent that's between 0 and 1, and that is going to give us a derivative that has a point where it's undefined. All right, so let's just be on the lookout for that. But again, first we're checking, is this function continuous on our closed interval? In fact, this is continuous everywhere. We're just taking cube root and then squaring it. Cube root is continuous everywhere. Squaring is continuous everywhere. That's just a polynomial right there, that part. So yes, this is continuous everywhere, specifically on the closed interval -1 to 3. So then let's take the derivative. So we end up with f prime of x equals 2 minus, we bring that down and we get a 2x to the -1/3. And we want to find out where this is 0 or undefined. I'm going to rewrite this as 2 minus 2 over x to the 1/3. And I'm going to get a common denominator here. Sometimes that helps me. So this is going to be 2x to the 1/3 minus 2 over x to the 1/3. That way we can see the numerator and find out where that equals 0. We can see the denominator and see where that will be 0, and hence the derivative will be undefined. All right, so let's take the top. So f prime is 0 when 2x to the 1/3 minus 2 equals 0. In other words, when 2x to the 1/3 equals 2, oops, 1/2. In other words, when x to the 1/3 equals 1, so that's going to be x equals 1. And then hopefully it's pretty obvious that the denominator is 0 at x equals 0. So I'm just going to write down here the critical numbers are x equals 1 and x equals 0. Again, we just do a quick glance here to make sure that those values are actually in our interval, which they are. All right, so we're going to set up an XY table here. We want to start with -1. Actually, it doesn't matter which order it is. Sometimes people put the critical numbers first and then the endpoints. Sometimes they do the opposite. I'm just going to do them from value least to greatest. So -1, then 0, then 1, then 3. All right, when we plug in -1 again into the original function here, we get 2 times -1 minus 3 times -1 to the 2/3. So 2 times -1 is -2. -1 to the 2/3 is going to be +1. Again, this is taking the cube root of -1, which is -1, and then squaring it, which is +1. So we end up with -3 here. And so we end up with -5. When we put in the 0, we get 0. When we put in 1, we get 2 times 1 minus 3 times 1 to the 2/3. Again, this is still going to be 1. So we're going to get 2 minus 3, which is going to be -1. All right, this one is not very fun. We're going to get 2 times 3 minus 3 times 3 to the 2/3. This is 6. And then this actually has an exponent of 1 or 3/3, so we could combine that to get 3 to the 5/3. All right, at this point, if you were doing it on your own, you would use your calculator to check it, but I've already checked it, and it's approximately equal to negative 0.24. All right, and so we are going to say then that, I just want to make sure I didn't mess up there. Okay, so that the min on the interval occurs here. And then interestingly, this is the max right here. All right, so min is at -1, -5, and then the max is going to occur at 0, 0. Okay, last one. Find the extreme of f of x equals 2 sine x. Sorry, let me make sure. Oh yeah, there we go. Okay, find the extreme of f of x equals 2 sine x minus cosine 2x on the interval 0 to 2 pi. All right, so we're going to check to make sure that we can actually use the extreme value theorem. And so we have got 2 sine x continuous everywhere, cosine 2x continuous everywhere. And so let's take the derivative of that. All right. So we've got f prime of x equals the derivative of 2 sine x is 2 cosine x. The derivative of cosine x, first we've got this minus in the problem. The derivative of cosine x is negative sine x. But again, we've got 2x, so I'm going to take the derivative of the outer function, so that's the negative sign. I'm going to leave the inner function alone, and then I'm going to take the derivative of the inner. All right, so we end up with 2 cosine x plus 2 sine 2x. And we want to find out where that's 0 or undefined. Right, it's never going to be undefined because cosine and sine are continuous everywhere. Right. I'm going to replace this with the double angle formula. Again, it's going to be much easier to solve for 0 if we're taking cosine and sine of the same angle. So instead of having that double angle there, I'm going to rewrite this as 2 cosine x plus 2, and then the double angle formula is 2 sine x cosine x. All right, so we've got 2 cosine x plus 4 sine x cosine x, and I want to know when this is 0. I'm going to factor out a 2 cosine x. So I get 1 plus 2 sine x equals 0. This is going to bring back all of your favorite memories from trig. Okay, I have a product of two things equaling 0. One of them has to be 0, so either 2 cosine x equals 0, or 1 plus 2 sine x equals 0. All right, so where in the interval 0 to 2 pi is cosine equal to 0? Again, this 2 is doing nothing for us right here, so we're just looking for where is cosine equal to 0. So that should be x equals pi over 2. And x equals 3 pi over 2. All right, at our up here and down here, if we're looking at our unit circle. And then here, this is saying where is sine x equal to -1/2. All right, negative occurs in quadrant 3 and quadrant 4. And those are pi over 6 angles. So in quadrant 3, the pi over 6 angle is x equals 7 pi over 6. And then in the fourth quadrant, that's x equals 11 pi over 6. All right, pause and think about that if you're struggling to remember it. All right, but those are the 4 points that we're talking about. Again, so these are the critical numbers, and then we have our 2 endpoints. And so we're going to make a nice big table here. All right, so we've got 0, we've got pi over 2, we've got 7 pi over 6. We've got 3 pi over 2. We've got 11 pi over 6. And we've got 2 pi. All right, so here's our x, here's our f of x. All right, so at 0, again, don't forget to go back to the original function. I'm going to write it down here so I don't have to keep sliding up and down. 2 sine x minus cosine 2x. All right, so at 0, sine is 0. And then, so we've got 0 minus, and then cosine of 0. Cosine of 0 is 1. And so we end up with -1 here. All right, when we put in pi over 2, we get 2 sine pi over 2 minus cosine of pi. Sine of pi over 2 is 1, so we've got 2 minus, and then cosine of pi is -1. And so we end up with 3. At 7 pi over 6, we've got 2 times sine of 7 pi over 6 minus cosine of 7 pi over 3. All right, 7 pi over 6, that is -1/2, times 2 is going to give us -1 minus 7 pi over 6. This is an angle in quadrant 1. Right, again, 6 pi over 6 would be the same as 2 pi, so we're up a third, pi over 3 again. So we're in quadrant 1. Cosine of a pi over 3 angle in quadrant 1 is 1/2. Right, so we've got -3/2. All right, let's come over here. 2 sine of 3 pi over 2 minus cosine of 3 pi. I'm going to choose this one first. Cosine of 3 pi, that is 0 pi, 2 pi, 3 pi. So here we're the same as when we were just at regular pi. That's -1. So that's going to be +1 here, or minus -1. Sine of 3 pi over 2, that is at pi over 2, so let's go 0. So this is -1, so this is -2. So we should have -1 here. All right, 11 pi over 6. 2 sine 11 pi over 6 minus cosine of 2 times 11 pi over 6. Again, this is going to give us an 11 pi over 3. So here we go. This is -1/2 times 2 is -1. Again, I know that because I just found out when sine was -1/2. It was up here. So minus, all right, 11 pi over 3 is, let's see, if it were 12 pi over 3, that would be 4 pi, which is the same as 2 pi. Right, so it's actually back here. We're just 1 shy of 12 pi over 3, so that takes us back here. Quadrant 4, cosine is positive, so this is a +1/2. Right, again, that minus comes from the equation. So we end up with -3/2 again. And then 2 pi. 2 sine of 2 pi minus cosine of 2 times 2 pi, or 4 pi. Sine of 2 pi is 0 minus, and then cosine of 4 pi, that is going to be the same as cosine of 0, which is 1, so we end up with -1. Okay, so the maximum occurs right here, and the minimum, there are 2, it's going to occur right here and here. So we would say the max, max is at pi over 2, comma 3. Min is 2 different places, 7 pi over 6, comma -3/2, and 11 pi over 6, comma -3/2. That was a whopper. Hopefully we won't see a ton of those, but if nothing else, hopefully it was a good refresher on some trig stuff. Please take your time and go back and look over that and really think about why I